Welcome back to the Deep Dive. Today, we're really getting into the practical side of things. We're opening up Chapter 5 from our research stack. And this chapter takes us past all the, theoretical debates about reinforcement learning.
Which we've spent some time on.
Exactly. And it drops us right into the messier, but absolutely crucial world of actually operationalizing RL.
Making it work in the real world.
For cyber operations. Specifically penetration testing. So we're trying to move this powerful tech off the whiteboard.
And into the digital trenches, so to speak.
Yeah, into the real networks.
And it really is the critical step, isn't it? I mean, we've established that RL agents can learn complex strategies. That's kind of the premise, right? But that ability is, well, frankly, useless if they're learning strategies for some kind of fictional environment. So the central issue Chapter 5 tackles is what the researchers call the grounding problem.
The grounding problem.
Yeah.
Okay. That sounds fundamental. It's this idea that the AI has to be, tethered to reality.
Precisely.
So, if you're prepping for a high-stakes, real-world deployment, why does grounding suddenly leapfrog everything else? Like, even developing a faster algorithm. Why is this number one?
Well, think about it. Computational speed means absolutely nothing if the data you're feeding the system is flawed, or if the system just misinterprets it.
Okay.
The grounding problem basically says that any AI or machine learning solution, before you deploy it, needs a formal representation of reality. And that representation has to be meticulously well-grounded, meaning it accurately reflects the actual live system it's working within.
Right.
Now, in academia, we love using attack graphs. They're neat. They're structural maps of network connections, vulnerabilities.
You're seeing all the time in papers.
All the time. But here's the critical insight from this chapter. The actual process of translating those abstract graphs and all the assumptions baked into them, translating that to a live, messy, dynamic network. That specific step has been seriously neglected in RL research.
Okay, so let me see if I get this. If I train an RL agent on, say, a perfect static attack graph, maybe one modeled with 100% accuracy on day one, the agent optimizes a policy that's perfect for that specific model.
For the model, yes.
But potentially disastrous when you deploy it in the live environment, which might have changed even slightly since day one.
Exactly. You've optimized for an abstraction, not for the reality it's supposed to represent.
Right.
So the reliability of any proposed RL-based cybersecurity solution doesn't matter if it uses proximal policy optimization, PPO for balancing exploration and stability.
Or A2C.
Or a synchronous advantage actor critic, A2C, known for its speed. Their reliability is fundamentally questionable if this model-to-reality link isn't solved first.
Those algorithms are powerful, right?
Right.
PPO, A2C, they let the agent explore complex situations efficiently.
They do, which is vital in a high-risk place like a network, but they're only as good as the environment, the simulation you actually give them.
So if the MDP, the Markov decision process, the agent's environment is faulty,
then the agent's learned policy will just lead it down a path of fictional wins. It thinks it's succeeding, but it's succeeding in a fantasy land.
Okay. So our mission today for this deep dive is really to dissect the architecture they're proposing to solve this grounding issue.
The layered reference model for RL agent grounding.
Yeah.
LRM-RAG for short.
LRM-RAG, got it.
Yeah.
And then we need to examine the big practical challenges, the roadblocks that stand in the way of actually deploying RL successfully.
Right. There are three main ones highlighted. Okay, so let's start maybe with the high-level view, the basic architecture that's supposed to make grounding possible.
Right.
And this isn't just about, plugging an algorithm into a network socket. It's much more involved. It's about providing a formal, pretty robust, multi-step process. The goal is translating raw network data into an environment that a machine can actually interact with and learn from reliably.
It sounds like we're building a kind of translation engine, like a really sophisticated interpretation layer.
That's a good way to put it.
Sitting between the cold logic of the RL agent and the chaotic reality of an enterprise network.
That's the core idea, yeah. The architecture defines this necessary chain of interaction. So at the top, you've got the RL agent. That's the intelligence, the decision maker.
Okay.
Crucially, it never sees the real network directly.
Never directly. Interesting.
It only interacts with the abstract world of the Markov decision process, the MDP.
Right, the MDP.
The MDP is basically the agent's universe. It's got the map, the rules, the rewards, everything the agent knows.
So the agent learns its optimal policy within this abstract universe. It figures out, okay, state X, then abstract action A, gives me the best long-term reward.
Exactly.
But that abstract action, action A,
Right.
it needs to be physically done somehow, right?
Right, and that's where the network interface comes in.
Ah, the translator.
Precisely. The network interface is the crucial translator. It's the point of actuation. It gets the agent's abstract policy directive like exploit host X via vulnerability Y, and it has to convert that into a concrete executable command, maybe a specific Metasploit module with certain parameters run against a specific IP.
Wow. The success of the whole thing really hinges on that interface working perfectly, doesn't it?
Absolutely. It's a massive potential failure point if not done right.
Okay, so the interface translates, sends the command, it gets realized in the real network. What happens then?
Well, the real network executes the command. Something happens. And that execution results in a measurable outcome.
Like
A change in state. Maybe a system gets compromised, maybe privileges get escalated, or maybe the connection just drops, or an IDS fires an alert.
so success or failure, or something in between.
Right. And this new state, plus whatever reward or penalty is calculated for that outcome, gets reported back up the chain,
Back to the RL agent.
back to the agent. And that allows it to update its policy, essentially learning through trial and error. But the key is that the learning is grounded in what actually happened in reality, not just in the simulation.
Got it. So that entire closed-loop agent thinks, interface translates, network acts, result feeds back. That's the foundational architecture.
That's the foundation, yes. #2. Deconstructing the layered reference model, LRM-DAG.
Okay, so that gives us the basic flow. But LRM-FAG, this layered reference model, must provide more structure, right?
Yeah.
To handle the complexity and the fact that networks change all the time.
Exactly. It adds the necessary layers of abstraction and definition.
So let's dive deeper into those layers. If we start at the bottom, the source of everything, where does the data actually begin?
It begins, as you'd expect, with the foundation, the real network processes.
The actual network itself.
Yep, the source of truth, the physical environment. We're talking live systems, network segments, firewalls, protocols, running services, data flows, all of it. Raw reality.
Messy stuff.
The very messy stuff. This is what the agent ultimately needs to influence.
Okay. From that chaos, the next layer up must impose some structure, right? That's the attack graph generation processes.
Correct. This layer takes information gathered from the real network, maybe through scans, config audits, vulnerability reports, that kind of thing.
Yeah.
And it uses that info to create a formal, structured representation, the attack graph.
The map.
The map, exactly. It lays out potential attack paths. It identifies vulnerabilities, what needs to be true before an exploit works the preconditions, and the state after a successful layered exploit, the postconditions. Sometimes it includes host information too. But the key thing to remember here is that at this stage, the graph is mainly structural.
It tells you what's connected and what vulnerabilities exist.
Precisely. What, not necessarily how or why or the rest.
Okay, so we have the structural map, but like you said, a map doesn't tell a general how to fight. We need more context, more intelligence. And that brings us to what sounds like the most complex part. The MDP construction processes. This is the engine room, where reality gets translated into something the machine can actually learn from.
This is really the core of LRM-RAG, I'd say. It's where we try to address that lack of behavioral realism you often find in simple attack graphs.
How does it do that?
LRM-RAG handles this by using 3 sequential, kind of stacked definitions of the MDP. Each one adds a progressively deeper layer of context.
3 layers just for the MDP. Okay, let's break them down. What's the base layer? Yeah. The broadest context.
That's the terrain MDP, definition 5.7 in the chapter.
Terrain MDP.
The terrain MDP captures the general environment. Think of it as the static, shared landscape that applies pretty much regardless of who the adversary is or what their specific goal might be.
So like the physical geography of a battlefield.
Exactly. The chapter explicitly draws on concepts from intelligence preparation of the battlefield, or IPB.
Ah, interesting. IPB for cyber.
Right, so this layer models things like firewalls not just as binary block-a-low things, but maybe as high-cost obstacles. Actions traversing them cost more or have a higher chance of failure or detection.
And intrusion detection systems.
Maybe modeled as a field of fire, a zone where attempting certain noisy actions drastically increases the probability of detection.
Okay, so the terrain MDP moves beyond just asking, is port 80 open? It asks, what's the risk cost of trying to use that open port 80?
You've got it. It introduces contextual risk. This MDP provides the baseline understanding of the landscape, representing general hardening, network segmentation benefits, choke points, etc. And a key benefit. Once you build this layer for a network, it's largely reusable across different red team exercises or scenarios on that same network.
That makes sense. You build the map of the landscape once. Then, building on that, we introduce the actor. Layer 2, the adversary MDP, definition 5.8.
Right. Now we tailor the environment to mimic specific threat actors. We're scoping the agent's potential actions and the likely outcomes based on who is doing the attacking.
How do you model an adversary in an MDP?
Well, the adversary MDP defines the action space based on the specific tools, techniques, and procedures, TTPs, associated with that attacker profile. You might use attack templates or known patterns.
So an APT group gets a different set of possible actions than, say, an insider threat.
Potentially, yes. Or, more often, it affects the probabilities.
The transition probabilities within the MDP.
Exactly. This is the primary way it manifests. If you're modeling a highly sophisticated, say, nation-state adversary, their transition probability for pulling off complex multi-stage exploits, probably high. It reflects their skill, their resources, their ability to bypass controls.
Okay.
Conversely, model a less sophisticated script kiddie. Their transition probabilities for those same complex actions might be near zero, but they might have higher probabilities for simpler, noisier stuff like default password brute forcing.
So this layer dictates how the fight is likely to be fought, based on the fighter's capabilities.
Precisely. If the terrain is the map, the adversary layer is the specific playbook and sort of the skill rating of the player.
That distinction feels crucial for getting realistic behavior out of the agent. Okay, terrain, adversary. Finally, we narrow it down to the specific goal. Layer 3. The task MDP, definition 5.9.
The task MDP is the final refinement. It takes the adversary model operating on the terrain and it specifies the precise penetration testing objective for this particular run.
And how does it specify the objective?
The chapter highlights two common effects. It reallocates the reward structure, or it rescopes the state space. Let's focus on the reward reallocation, as that's really how you steer the agent's learning.
Right. Rewards are everything in RL. Give us some concrete examples. How would different tasks change the reward?
Okay, sure. Let's say the task MDP specifies the goal is gaining persistence.
Right. Staying hidden long term.
Right. So the reward structure might give a small positive reward for every successful host compromise just to encourage exploration. But the massive positive reward, that's reserved only for the state where a backdoor or some persistent remote access mechanism gets successfully established. And importantly, maybe on any system, even low-value ones initially, because persistence itself is the goal.
So the agent learns to prioritize long-term, maybe covert survival over just grabbing lots of boxes quickly and noisily.
Exactly. Now contrast that with a task like crown jewel analysis.
Okay, going after the high-value target.
Right. For that task, the reward function might be almost inverted. The agent gets maybe 0 reward or even a tiny penalty for noise for compromising 3 perimeter web servers.
They're irrelevant to the goal.
Totally irrelevant. However, achieving privilege escalation on that one, specific designated database server holding the critical IP, that results in an immediate exponentially large positive reward.
So the agent learns to ignore distractions and path directly to the objective, maybe even accepting higher detection risk along that specific path if needed.
Precisely. The task MDP ensures the agent's learned policy directly serves the specific human-defined red team goal for that engagement.
The modularity here is, well, it's really quite smart, isn't it? The terrain, network map, and the adversary profile, threat actor TTPs, can be built and reused, meaning maybe only the task MDP, the objective, needs to be redefined for each new pen test.
That's the elegance of the LRM RAG approach, exactly. And this systematic layering brings us to the fourth main process block in the model, the machine learning processes.
Okay. We've established the core RL agent is the one learning the policy from these layered MDPs. But there's also this more advanced concept mentioned, the meta-learning agent, definition 5.1. Why do we need another agent? The learning-to-learn agent.
Good question. We need it because enterprise networks aren't static. They're inherently dynamic.
Things change.
Constantly. A major security patch gets deployed network-wide. A new server segment is brought online and isolated differently. A firewall rule changes. When that happens, the terrain MDP suddenly becomes inaccurate.
Right. The ground truth shifted.
Exactly. And without something like a meta-learning agent, the entire potentially weeks-long training process for the main RL agent might have to restart from scratch every time reality shifts significantly.
Which would be computationally crippling. just not feasible operationally.
Totally infeasible. So the meta learning agent is designed to mitigate that. It uses techniques like, say, transfer learning.
To quickly adapt the RL agent's existing knowledge.
Precisely. Adapt its knowledge base to the new circumstances without starting over. If the agent learned how to compromise, I don't know, an old version of Linux, and now a new patched version is deployed, the meta learning agent helps facilitate rapid adaptation. It learns how the knowledge from the old network state maps onto the new one. It ensures the RL agent doesn't have to relearn basic concepts like what is SSH every single time.
Okay, so it's about efficiency and adaptation. Section 5.2.5 in the chapter kind of summarizes this synergy, right? The layering plus the meta agent provide a formal system for transferring knowledge across different tasks and changing environments.
That's the goal, yes. A framework for reusable and adaptable learning.
It sounds incredibly thorough, but the authors are careful, in Section 5.2.6, to point out what LRM-RAG doesn't do. What are the acknowledged limitations?
Well, first, it's presented as a general framework for grounding. So by design, it consciously avoids defining the absolute specifics of the state space, the action space, the reward function.
Why avoid those? They seem pretty important.
They are crucial. But the chapter notes these are still varied and evolving research topics. The community just hasn't settled on universal standards for how best to define states, actions, and rewards for CyberOps RL. So LRM-RAG leaves that open.
Okay. And it also mentions it doesn't explicitly model the specifics of entire penetration tasks or campaigns. We saw the task MDP defines a goal, but maybe not the whole sequence.
Exactly right. The task MDP defines the reward for achieving a single objective, like gain persistence or access crown jewel, but it doesn't inherently manage the complex, multi-stage workflow of a full campaign.
Like pivoting from persistence to lateral movement to data staging to exfiltration.
Right, that necessary orchestration, managing the transitions between different task MDPs or objectives within a larger campaign. That's where the concept of whole campaign emulation, WCE, comes in.
WCE?
WCE is framed as the longer-term goal, the thing needed to fill this gap. It would be the framework for automating the complete adversarial workflow, presumably using the grounded environment provided by LRM-RAG as its foundation.
So LRM-RAG provides the grounded sandbox. WCE would provide the multi-stage play calling.
That's a decent analogy, yeah. Hashtag TechTech3, key challenges for operationalizing RL.
Okay, so LRM-RAG gives us the theoretical blueprint for grounding. But getting it deployed in the real world means tackling some huge practical obstacles. Let's shift gears now to those three primary roadblocks mentioned in the research. The ones preventing RL from being, everywhere in live CyberOps today. The first one is generation and actuation. This sounds like it's about making the agent's learned strategy actually happen.
Yes, this is maybe the most immediate, boots-on-the-ground operational hurdle. The core issue is that translation component we talked about earlier, the network interface, the actuation component.
The translator between abstract and concrete.
Right. The agent calculates an abstract action, do exploit A, but the interface has to translate that into a concrete runnable action or sequence of actions in the real network, and it has to work reliably.
And the requirements for that translation must be incredibly strict, right? You can't just be a simple API call. It needs context.
Oh, absolutely. It needs to be context-aware.
Yeah.
Robust enough to handle all the weirdness of real networks, delayed responses, unexpected errors, slight variations in system configs.
Yeah.
I mean, think about the difference between the agent deciding execute exploit X and the interface actually having to figure out the target OS version, find the right payload encoding, determine the egress path, maybe time the exploit carefully to avoid a specific security control.
And then manage the execution and parse the result.
Right. It's a massive engineering and operational lift to build that reliably.
And research points out that even how we build the MDP environment in the first place affects how reliable that actuation can be. It contrasts two main approaches.
It does. So approach one, common in academic work, uses existing tools like Molval.
Volva.
Yeah, it automatically generates a full attack graph based on network scans and vulnerability databases. It spits out the graph, then you build your MDP on top of that.
Okay, automated generation. What's the second approach?
The second approach often bypasses that kind of fully automated graph generation. It relies more on network attack simulators or even handcrafted models. These are often used in commercial red team tools or specific research platforms.
And why does relying heavily on tools like Molval create a specific kind of problem, vulnerability, so to speak?
It can create a vulnerability bias. Molval and tools like it tend to rely heavily on vulnerability scoring systems. Specifically, the Common Vulnerability Scoring System, CVS.
CSS scores, right? We hear about those all the time.
Oh. They're used to populate the attack graph data, what exploits work, how severe they are. So if your whole environment, your MDP, is built primarily on CVSS data, then the policy your RL agent learns will inevitably be heavily biased towards addressing known vulnerabilities, specifically the ones with high CVSS scores, the documented CVEs.
I might systematically ignore threats that don't have a nice, neat CVSS score.
Exactly. Threats relying on, say, network misconfigurations or human factors like weak passwords or zero-day exploits that haven't been assigned a CVE or score yet, they might just not show up prominently or at all in the model.
Which leads directly into the second big challenge.
Challenge 2. Realism.
If our environment is built mainly on known, scored vulnerabilities, our RL agent isn't training against a realistic, adaptive adversary, is it? It's training against a static checklist.
That's a great way to put it, a static checklist. CVSS is a critical metric, don't get me wrong, but it focuses almost entirely on technical severity.
Like how easy is the vulnerability to exploit, and what's the immediate technical impact, code execution, denial of service?
Right. But CVSS scores inherently struggle to account for crucial contextual factors, such as the strategic value of the asset being targeted, the presence of other compensating security controls around it, the specific industry sector maybe, the attacker's actual motivation and goals.
So a vulnerability could have a critical CVSS score, technically?
Technically critical, yes. But if that vulnerable system is sitting isolated behind 5 layers of firewalls and holds absolutely no critical data, the actual real-world risk might be quite low. CVSS alone doesn't capture that nuance well.
And that technical bias must make the policy learned by the agent fundamentally flawed for real-world use. It might waste time on technically severe but contextually irrelevant vulnerabilities.
Or worse, miss a low CVSS vulnerability that happens to be on the direct path to the crown jewels.
So how do we fix this? How do we correct the agent's view of the world to make it more, well, realistic?
The proposed solution comes right back to the LRM-RAI structure we discussed. It's the incorporation of those cyber terrain concepts.
From the intelligence preparation of the battlefield stuff.
Yeah.
Into the MDP construction.
Exactly. Using that terrain MDP layer. This is really the key insight, especially for defenders, for blue teams trying to model attacks.
Okay, so we stop rewarding the agent purely for technical achievements, like popping a box with a high CVSS score, and start rewarding it or penalizing it based on strategic success, considering the contextual risk defined in the terrain layer.
That's the idea. By layering in the terrain MDP, you try to balance that technical bias from CVSS. You model the environmental constraints, the detection probabilities, the costs of traversing certain network segments.
So, an example, an agent compromises a server with a critical CVSS vulnerability.
Yep.
But UT, doing so triggers a highly sensitive IDS alert protecting the critical data segment right behind it.
Okay.
The contextual penalty assigned by the terrain layer for tripping that specific alert might outweigh the technical reward from the compromise itself.
So the agent learns, okay, that path is technically possible but strategically bad because I get caught. Exactly. It discourages the agent from using that noisy path again, even if it worked technically. It forces the agent, hopefully, to learn stealth, strategic planning, path selection, mirroring how a realistic human adversary thinks. They worry about getting caught, not just racking up CVE scores.
So meticulous reward engineering, factoring in this terrain context, becomes absolutely essential. Not just an optimization, but a requirement for achieving realism.
It really does. Which brings us smoothly to the third big challenge.
Challenge 3. Unstable and evolving networks. Even if we nail actuation and realism, the ground itself is constantly shifting beneath the agent's feet.
This is maybe the ultimate long-term challenge for making RL work reliably in cyberops. Enterprise networks are not static labs. They're living ecosystems.
People join and leave, changing user accounts and permissions.
Systems get patched, configs get updated, new applications are deployed, user behaviors shift. It's constant churn.
So if the network changes,
then the RL agent is, at least temporarily, grounded to an out-of-date representation of reality. The MDP it's using is suddenly wrong.
It's like trying to navigate a city using a GPS map from last year.
Perfect analogy. The route calculated might seem optimal on the old map, but in reality, it leads you straight into a new construction zone or a road closure.
And the research paper articulates this timing problem using the concept of 2 very different loops of interaction. This seems important. We should probably slow down and really unpack this timing discrepancy.
Yeah, this is critical to grasp. Let's start with the smaller loop.
Okay.
This is the RL agent's internal world. It's where the agent interacts only with the abstract attack graph, the MDP model it has. Once that MDP is constructed, the agent's search for the best path, the optimal policy, is purely computational. It's just math inside the computer.
And it could be incredibly fast.
Blazingly fast. It could run thousands, maybe millions of calculations per second, exploring states, updating values, converging on a solution, potentially, every millisecond or so for simpler updates. This is the silicon brain searching its internal map.
Blistering speed. Now, contrast that with the larger loop.
The larger loop is the feedback mechanism that's tied back to the real world. This is where the agent's findings might inform actual changes.
Like the blue team hardening the network based on a path the agent found.
That's one possibility. Or just the underlying network configuration changing due to normal IT operations, patches, user activity, etc. The key is the rate at which the real network environment is scanned, modeled, and refreshed into a new attack graph, a new MDP.
And that refresh rate is much slower.
Dramatically slower. Maybe in a large environment, you can realistically rescan and rebuild the model every 30 seconds, maybe every few minutes. It depends hugely on the scale and complexity.
Okay, so let's put numbers on it. Agent finds an attack path computationally in, say, 50 milliseconds. But the attack graph, the MDP it used, only gets refreshed from reality every 30 seconds.
Right.
That means for 29.95 seconds, the agent is operating on potentially stale data. It might be optimizing a policy based on a vulnerability that was actually patched 10 seconds ago, moments after the last scan finished.
That's precisely the operational risk. The agent is effectively flying blind to reality updates during its fast internal search cycles.
It creates this window of vulnerability, or maybe a window of invalidity for the agent's actions.
Yeah, invalidity is a good term. The agent executes a path that looks optimal on its outdated map, but in reality, that path is now blocked, ineffective, or worse.
Worse how?
Worse, it leads to immediate detection because the defense, the terrain, has already changed in a way the agent doesn't know about yet.
Wow. Bridging that timing gap seems absolutely essential for stability. How do you even do that?
Well, the chapter doesn't offer a silver bullet, but it points towards areas of research. Maybe techniques that force more synchronous updates between the loops, or maybe incorporating confidence scores into the attack graph segments. How sure are we this path is still valid?
And this is also why that meta-learning agent becomes so crucial again, right?
Exactly. It's designed in part to help the main RL agent cope with these rapid environmental shifts more gracefully without completely failing or needing a full restart every 30 seconds. Mitigating this dynamism is key. #hashtag by V. Conclusion and takeaways. So to kind of pull all of this together from Chapter 5, what we've established is that operationalizing RL and CyberOps isn't just about better algorithms. It's fundamentally a challenge of abstraction and reliability.
Getting the model right and keeping it right.
Exactly. And the research gives us the LRM-RA model as this generalized framework for structured grounding. It dictates the step-by-step process needed to try and turn that complex, dynamic reality into a controllable, learnable environment for the agent.
And the really clever insight of LRM-RAG seems to be its modularity, the way it uses those layered MDPs.
Right, which allows, theoretically, for more efficient knowledge transfer and more targeted policy learning.
We identified those 3 key layers for the MDP. The foundational terrain MDP, capturing the static landscape, the contextual risks, the IPB-like elements. Then the adversary MDP, defining the specific attacker, TDPs, and capabilities, mainly through adjusting those transition probabilities.
Right, modeling who.
And finally, the task MDP, which focuses the agent on the specific objective for this run, usually by tweaking the reward structure.
Yep, the what or why. But as we discussed, this elegant framework is only going to be truly viable if the field can overcome those 3 major operational hurdles we unpacked.
Hurdle 1, actuation. Needing that flawless, reliable network interface to bridge the abstract policy and the concrete network actions.
Critical. Hurdle 2, realism. Demanding we move beyond just technical CVSS scores and incorporate that contextual cyber terrain into the models and reward functions so the agent learns realistic strategic behavior.
And hurdle 3, dynamism and grounding. Needing solutions to mitigate the risks from unstable, constantly evolving networks, especially that timing discrepancy between the agent's fast internal search and the slower refresh cycle of real-world data.
Those are the big mountains to climb.
This systematic approach, breaking down the attack modeling into terrain, adversary profile, and task or goal, strikes me that this isn't just useful for training a red team agent. It seems like a really valuable lens for the blue team, too.
Oh, absolutely. How can you defend effectively if you don't understand how the adversary is likely to perceive the environment and plan their actions?
Understanding how the automated adversary is being trained seems like it would directly inform how the defense should be prioritized.
Precisely. The layers of the LRM-ARAG system, terrain, adversary, task, they aren't just computational constructs. You can think of them as strategic dimensions of network security itself.
They offer a way to model what success looks like for different kinds of attackers pursuing different goals within your specific environment.
And conversely, they can help you analyze where your defensive investments might yield the highest return against those modeled threats.
Okay, so that leads perfectly into our final thought for you, the listener. Building directly on this strategic power of the layered MDP concept. If this layered model is key to training potent automated adversaries, and knowing that defensive resources are always limited, where would you choose to allocate your defensive efforts for maximum impact?
Think about it.
Would you prioritize investment at the terrain layer, focusing on making the general landscape fundamentally hostile to any attacker? Robust segmentation, strong perimeter defenses, maybe network deception technologies, make the map itself hard to navigate. Or would you focus more at the adversary layer, investing heavily in threat intelligence, rapidly detecting and blocking specific known TTPs, IOCs, attack patterns associated with the adversaries you care most about? Focus on the player's known moves.
Well, perhaps.
Or maybe you concentrate your efforts primarily at the task layer. Intense monitoring and defense specifically around your identified crown jewels, critical data exfiltration points, and known high-impact objectives. Defend the ultimate goal.
Where do you put your chips? Terrain, adversary TTPs, or task objectives? Analyzing your own risk through those three lenses might bring a kind of strategic clarity that just looking at technical controls alone often misses.
Something to definitely mull over. That's it for this deep dive into the architecture and the very real challenges of operationalizing reinforcement learning for cyber operations. We hope this gave you a bit of a strategic shortcut to understanding where this field is heading.
Yeah, the potential is huge, but the path to get there is, well, non-trivial. Join us next time as we continue to explore the cutting edge of research.
We'll see you then.